Hello, this is Paul from Fossil Tech. In the last lecture, we dealt with the classical problem of slope, and this lecture we deal with another classical problem. So we call the instantaneous velocity. And both of the questions, you a little bit later you will see we have to use the same strategy, okay, which is the idea of a limit to solve the problem. Okay, let me show you the question first. So here the instantaneous velocity. Okay, the idea is like this. So the question is this. Let me first look at the question. Okay, I'll draw here. You can see. Suppose we have this straight line. Okay, a particle at here, object. Okay, so at here, which is the t equals 0 seconds, and for example, the particle moves on a straight line, move forward in this direction. Okay, we suppose at 10 equals second. Okay, at 10 equals seconds, the particle moves here. Okay, is t equal 10 seconds, and our object or this particle moves sometimes faster, sometimes slow. Okay, does not keep the same speed or velocity. Now our question: how do you find the speed or the velocity at the specific time point that t equals 10? I mean, how fast? Okay, the object at t equals 10. Have we solved this question before? This we call the instantaneous velocity at the specific time point. We never defined this before. Okay, in in high school or middle school, whatever, we never defined. But we did what? We did it for average velocity, right? Okay, the change in distance over the change in time is the average velocity. Yes, we can use that basic definition. Okay, we can use average velocity to define what is the instantaneous velocity, and later you see the idea is like a limit. So how do you? So for example, we have this. If t equals 11 seconds, the object moves here already. Okay, so what do we have? So we have like this. We have from this point to this point. Okay, and we can definitely find the average velocity between 10 seconds and 11 seconds, right? We say average velocity, I use v1, but this is the average velocity. And how do you find the average velocity? The distance, the change in distance over the change in time. Okay, so we can find the average. I can use this average to approximate what is the velocity. Of course, the velocities are here. What is the velocity? Okay, at a specific time point. This is the instantaneous velocity. From this graph, you can see the instantaneous velocity can be estimated by this average velocity. But this approximation, is not good. We can make it better. How? We can shorten the time period. Okay, the time increment is 1 second. So we can look at 0.5 seconds or 0.1 seconds. Let me see. If I simply say here is the object, probably can do this. Okay, so I stop at here. I look at the time increment is like 0.5, half a second. The object from here move to there. Okay, so we can find another average velocity. So we say it's a v bar 2. Can you see this? Okay, the same. We also can find the v bar 2, but this time the approximation should be better. Okay, so the approximate v, the velocity at the time point, v2 is better than v1. Okay, you can imagine. If we want to make it much better, we can shorten again. If we do this, okay, this object move to here. I mean, they move very short time, and the distance moves also very short. Is v3, and we say is v bar 3, and do approximation. This one is better. v3 bar is better than v2 bar, better than v bar. Okay, move on. You can say Okay, v3, v4, v5, v100, v1000, we can do what? We can get the definition, the approximation is better as better, right? So how do you say that? So we can do this. How do you find this? We can use the limit. Okay, we can use v1 bar, v2 bar, v3 bar, dot dot dot. Okay, all this. What does it mean? I mean, we can use this sequence. Okay, we can use the limit of this average velocity to approach the instantaneous velocity. Okay, this is the basic idea. It's very similar as the slope, right? So we use the limit. Okay, these are we call the limit idea. Okay, the idea we call the limit. So you can see, we can use this limit idea. Okay. We have another understand. So wait a little. Okay, so here, so you can see. So we just say the instantaneous velocity can be defined by the limit of the average velocity. Okay, on the graph I showed you. And we have another understand, which is there. I showed you a remark. The instantaneous velocity is the slope of the tangent line of the distance function. Okay, which means what? And later we will merge this instantaneous velocity to the slope question, so we have the same, okay, the common format. How to understand that is this: we draw a function, and this function we call it the distance function. What does it mean? Okay, when t equals 0, this axis is t, of course. When t equals 0 and the distance, okay, the positions at the origin is 0, and then when the time move on and the particle moves, the distance gets larger and larger, which means the particle move forward, right, as the timer moves on. Okay, this is the distance function. And our questions now, we can look at this at a specific time, or here we put t equals a. What is the instantaneous velocity? We still are going to solve the same problem. Okay, how? And we need to use this. Okay, what we just get is we use the average. We use the limit of the average velocity. We need to find the average velocity. Where? Okay, average velocity in this one we set at the delta t, or the time increment, or the change in time is h. So from t equals a, now the particle moves to the time t equals a plus t plus h. From the original, the distance function at here now moves to the distance functions go to q, from p to q. Can we find what is the average velocity of this object? Yes. Average velocity is the change in distance, which is delta y, over the change in time, right? Change in distance over change in time is average velocity. See, delta y over delta x. What do we get? We get the slope of this. Is, of course, you know, this is the secant line. We can definitely find the average velocity is the slope of secant line. See, we go back to the last topic. Okay, it's exactly the same. Then now, can we look at the second graph? Okay, what is the instantaneous velocity now? Do you remember here? Instantaneous velocity is the limit of the average velocity, which is the limit of the slope of the secant line, which means what? H approaches 0, which means the point Q approaches to the point P, and the secant line, the finally approach to, okay, the tangent line, which means the slope of the tangent line exactly is the instantaneous velocity. That this makes sense? Okay, the limit of average velocity is the limit of the slope of the secant line. Therefore, is the slope of the tangent line that we call it the instantaneous velocity. Okay, just from that result. Okay, so now both questions, both classical questions merge to the same. Okay, what is the slope of tangent line? Is the limit of the slope of the secant line? What is the instantaneous velocity? Is the limit of the average velocity, okay, on the distance function. right? It's exactly the same. I have one question to show how to use this definition. Okay, average velocity we found first, and then we're going to take a limit, okay, or look at the pattern. So now I have one question to show to you. So here's the question. Wait, so let me get this so you can see all the questions, right? What the questions? Okay, it is if a ball is thrown into the air, okay, with a velocity of 40 feet per second, and its height in feet t seconds later is given in this water. This is the distance function. Now we know the distance function or the position function or the distance function, right? We have two questions. The first question is to find the average velocity for the time period beginning when t equals 2 and the lasting 0.5 or 0.1 or 0.05 or 0.01. What does this mean? So then we're going to write the time period interval. Okay, so I wrote the interval first. Okay, t equals 2, less the 0.5. If the last 0.5, I wrote it into the interval is this. From time 2 to 2.5, right? See? And the t from 2 to 2.5, and we definitely can find what is the average velocity. Use what? Use the distance in, use the change in distance over the change in time. The change in time, this time is the less than time 0.5, the same. If less than time is 0.1, now the average velocity we need to find is between 2 to 2.1, right? 2 plus 0.1 is 2.1. And here the third question should be, the third part should be this, from 2 to 2.05. Find the average velocity. And the fourth is this, and from 2 to 2.01, right? So this should be from 2 to 2.001. Okay, and from this you can see the lasting time approach 0, which means what? The average velocity will get closer and closer to this question, instantaneous velocity, we just explained. Okay, so we finish this part and then we can finish the second part. Estimated the instantaneous was the instantaneous now. And the instantaneous should be like this. Okay, it should be the limit. Do you remember we just did? Instantaneous velocity is the limit of the what? Average velocities. Average velocities. Which means what? We can use this to find the instantaneous velocity. We add the average velocity part A, we find all this. Okay, and then we look at the pattern. So now we can go into the first part. So how to find all the average velocity? We will build the table. Okay, so like we did before, we're going to build a table. But what is the average velocity? What the function? What do we need to do? We need to define what the function first. Let me define what the function. So for the first part, okay, and if I simply say the average velocity, and for specific time period, for the time period we set up from 2 to 2 plus delta t. Delta t is the time increment. Okay, and then now we need to get a general formula. Okay, because we just see delta t should be 0.5, 0.01, 0.05, 0.001, 0.001, right? So later we will change delta t and to find the change on the average velocities. So we find the general formula. And the general formula should be like this. We're going to find the general formula is I use V bar. Okay, V bar is the average velocity between this time period, which is we can find should be this. The change in distance, or we say is delta, you know what that data mean. The change, okay, change in the distance. Okay, this is the data time, which means the change in time. Change in time is delta t, right? Exactly delta t. The change in distance is the distance functions between 2 and the 2 plus delta t. Okay, so now what we're going to do, I use the definition. Okay, here. What is the change in the distance? Is s added the last is 2 plus delta t. See, this is the position minus the previous position at t equals 2, which is s at 2, a bit longer. And then what do we need to do? Divided by the distance, the change in time, which is delta t. Okay, now move on. I will going to put the function. I will going to write a little bit long calculation this time. Okay, so what is s? Let me going to find the function here. Okay, so can you see? Okay, s is here. We're going to evaluate s at 2 plus delta t, and evaluate s at t. Just evaluate the function. Okay, so I copy here. We evaluate at that, which is 40 times 2 plus delta t minus 16 parenthesis 2 plus delta t square, and this is for s at 2 plus t minus s at 2. Of course, you have to do calculation. S at 2, replace t by 2 and do calculation. What I get? I can get a 16. Okay, so this one is just a 16. Good. And then the bottom is the delta t. Now I will going to do calculation. So do calculation, what do we get? So let me look at it. I will going to do calculation here. So can we do calculation? Okay, so what do we have that? 40 distributed, which means we get a 80 plus 40 delta t, right? Minus, okay, we have a parenthesis, don't miss. This is the perfect square. Let me write one more step. So 16 is the upper here, and I expand this perfect square, which is 4 plus 4 delta t plus delta t square. Okay, minus 16. And then I distribute the 16 inside. See what do we get? We get 80 plus 40 delta t minus 64 minus 64 delta t minus 16 delta t square minus 16. I will put this, the first put here 16 delta t square. How about these two? And this I combine the like term. So this should be minus 24 delta t, right? Good. Minus 24 delta t. And then another is the constant 80 negative this, put them together is 0. Okay, just plus 0. Can you see? Almost there, right? This is the top, of course. This is the top, and later we need to use this word divided by delta t. Can you see this? The bottom is this divided by delta t. Of course, I will use this minus 24. This is the top over delta t. You can imagine what do we get? Okay, factor the delta t out, and then you can divide it out delta t. So we should get this. We should get a negative 16 delta t minus 24. Okay, so this is the one. I copy here. That's what we got. We just do calculation. So after the calculation, wait, I just get is negative 16 delta t minus 24. That's good. So this is the first step. So we already built the function for the average velocity depending on the increment of the time. So now we're going to evaluate these functions at a different delta t, okay, on a table as we did before. So like this. This is a table. Okay, and how to evaluate? All we need to do use the calculator, right? So we're going to use the calculator. So like which calculator to use? The function and the table in calculator, right? So I will write here. We did this in the last topic. Okay, I was going to use function and the table in calculator. The Texas Instrument 83 or 84 to find what is here. Okay, what is the average velocity? We just have the function. If someone you don't like to use the function or the table in the calculator, all you need to do is what? Plug this delta t to here and do calculation to find the v, average velocity. However, I just use the functions. So what do we need to do? I will first define the function. What is the average velocity? Define the function this in the calculator. The second step, plug this in the table and apply the function to find what the value of the average velocity. Let me show my calculator. I'll set up my calculator for you. So here is my calculator. Can you see? Okay, so my Texas Instrument 83. I open mine. So the first step, we define the function. You also need to do that, right? Where is my function? So my function is here. Okay, so I defined it that this is average velocity function. Okay, average velocity function here. We define this in the calculator. So find the y equals. Let me tune first. Hold. Yes. The function is negative. Negative is here. Okay, negative is not a minus. Negative 16 times delta t, right? 16 times delta t. We get. Let me see. Delta t. So delta t here we cannot use delta t, but we can use x. Okay. The alpha beta x. So in the function we have to do this. Negative 16 x minus this time is here 24. Remember this function we just did. This is the average velocity function. Negative 16 times x. Here in the calculator we have to use x minus 24. So we define the function. Good. The second step, what do we need to do? We need to find the value of the function, right? So we need to define what is the variable. I define this variable in the table in calculator. The table is going to stat. Okay, edit. There's an enter data. Can you see this is the table? So I will put the x value in the first column, which is L1, and then going to apply the functions on L1 to get the y value on L2. Okay, what is L1? I will going to type all the lasting time, which is data 0.5, 0.1 like this. Okay, so going to 0.5, 0.1, 0.05, 0.01, 0.001. See, it's good. I put all the x value there. Now I will move to the top of L2. Highlight. What are we going to do? We're going to find all the velocity, average velocity on this time. Okay, so now we have to find the function. Applying the average velocity function on the first column. Going to find its variable. Go to right. Go to function, and the y1. It is we need. Okay, so now y1 at L1. How do you find the L1? Second one, which is L1. Parentheses. Can you see these functions is exactly the average velocity, right? And so all I get is this. I will copy this y value to here. So we finish this table. So let me copy the weight. So I got my it's here. We get Okay, so I think you can see all right. Let me copy. So all the values here is negative. You cannot see. Is negative 32. So the first negative. Let's see. Negative 32 is the first. The second is negative 25.6. 5.6. The third is negative 24.8. What does negative mean? Okay, negative means it goes down. Okay, positive we define as it goes up. Okay, the object moves down, so we have a negative velocity. Don't worry. Okay, so they are copied. Negative 24.16.16 and negative 24.2, 24.02. Sorry, that's good. See, we just get from here a copy from the paper to the paper. Now, what are we going to do? This is the first question, right? The first question we answer all the average velocity. The last is the second part, right? So all we need to do is the last part, the part P. B asks us what is the instantaneous velocity at the time t equals 2, okay, which means the pattern. Do you remember? Instantaneous velocity is the limit of the average velocity, or the pattern. What is the pattern? The pattern tells us all this number gets closer to negative 24, which means we can guess negative 24 is the instantaneous velocity. Okay, so we can do this. Now, we can say about the pattern. We always say the pattern, right? That's good. And now the instantaneous velocity. Let's say. Which means the velocity at what? At t equals 2. Okay, so I use v to describe. Now is negative 24. What is the unit? Is feet. Sorry, the feet per second, and that's all. Thank you.